Hello Science Alliance, hello my IGCSEers, I'm Lara, this is Theatre of Science, your Science Alliance. We're doing IGCSE, the third lesson of the whole module. It's going to take 2 years. This is just lesson 3, speed time graphs. So last week we looked at distance time graphs and I thought we'll just do a little recap. So do you remember, if you've got distance on the y-axis pointing up the sky, time on the x-axis, we were looking at what happens if you've just got a straight line on your distance time graph. So if you've got a straight horizontal line like that, what's happening? What is happening? Time is going by, but distance isn't changing. So a distance time graph that looks like that would be something that was staying still, okay? Whereas the ones that we looked at a lot were these diagonal lines. And we were saying how speed, the equation for speed is distance divided by time. I'm just going to write d divided by t. So you can use what's called a gradient. Do you remember this? So most of you know how to do this already. Use a gradient to work out the speed. So you can just draw any triangle around your line and use the height of this bit, because that's the distance, right? If you go across here like this, that could be, I don't know, could be anything, couldn't it? Could be 4 meters. And then divide that by this bit of the triangle at the bottom, which is however many seconds that is, and then you would have your speed. Do you get me? So that's called the gradient of the line. Draw any triangle around it, do the distance, which should really be on the y-axis, divided by the time, which should be on the x-axis, and you get the speed of the thing. So this was something that we said was travelling at a constant speed. If it's a distance time graph and you've got this straight diagonal line, that means that it was going at the same speed every time. Wherever you take the gradient of that graph, you will always get the same number, right? That divided by that is the same as that divided by that. So what speed was this object going at? It was a trick question, sort of. Did you ever look at your units? So you might have been tempted to say, okay, well, speed is distance divided by time. So I can see already, like if I draw any kind of triangle here, I could do 3 divided by 3, which is 1, or do my triangle there, 2 divided by 2, which is 1. So the answer was going to be 1, right? So you might have said it was B, 1 meter per second. But look at the units. The distance is in kilometers and the time is in hours. So the answer would have to be 1 kilometre per hour, because that's what your units are. And there is no option for 1 kilometre per hour. So the answer must have been 0.9 kilometres per hour, because maybe, and this is why teachers are always shouting at people to use sharp pencils when they draw lines and graphs and things. Maybe this isn't quite one. Maybe we read this wrong. Maybe because this line is very, very thick. Maybe if you took the gradient very precisely, you would get an answer of 0.9. So it had to be 0.9. Right. Ofsted would be delighted. This incredibly stimulating, exciting start of the lesson. What I've done is I've got 3 tables, 3 distance time tables. What I want you to do is roughly sketch a distance time graph for each one. If you have been to my website, then you might have got the printouts for this lesson, and I gave you the axes, which is pretty good of me. If you haven't got the printouts, don't worry about it at all. Just roughly sketch it. I mean, using a ruler might be a good idea, but it doesn't really matter. I just want you to try and get a feel for the shape of each of these graphs, okay? And I've said if you're finished, if you're one of these like, oh, I'm finished, this is boring people, well, then in that case, can you add a 3rd column to this table, please? And call it speed. So that would be speed in meters per second. And can you fill it in? So what was the speed of this thing at 0 meters after 2 seconds? So it's distance divided by time, right? So it would be 0 divided by 2 equals whatever. Fill that in. So you've got a speed column. Is that all right? So the first table, you've got the distance is 0, 3, 6, 9, and the time is 0, 1, 2, 3. The second table, you've got a distance of 0, 1, 2, 3, and the time is 1, 3, 5, 7. And the third table, the distance is 0, 3, 8, 15, and the time is 2, 3, 4, 5. Some of you will be able to spot some patterns here anyway. So I'm being very annoying, just shuffling your little quiz questions for the end of your lesson around behind you. It smells amazing in here because I just got my sourdough bread out of the oven and put it on display behind me. I'm big worried I haven't cooked it far enough. There's no going back now. You can't put it back in, can you? It's supposed to sound hollow. Does that sound hollow? Doesn't really, does it? I will see. Have you sort of more or less done that? Obviously, you can always pause this, can't you? If you're not watching live, obviously you can. You're probably not even listening to this. You probably just paused it and then skipped ahead. If you're watching live, it doesn't really matter if you haven't finished it, does it? Shall I go through the first one? Maybe while you're just finishing off the last one, I'll go through the first one. So, for the first one, obviously you've got to make sure that your axes can manage all of the numbers. So I've put my distance going up to 9 metres and I've put my time going up to 7 seconds. I hope that you've, well, I did just say to sketch it, didn't I, actually? So if you haven't put in your labels and your units, I suppose that's fair enough. But anyway, if you plot those points, you've got 0 and 0. 0 time passes by, zero distance. And then after 1 second, this thing had travelled 3 metres. After 2 seconds, it had gone 6 metres. And after 3 seconds, it had gone 9 metres. So, I mean, you might have just been able to see that because the time was only going up in seconds and the distance was going up 3 metres each time. So a lot of you will have just been able to look at that and say, well, it's going at 3 metres per second. It is going at 3 metres per second because, yeah, I can just see that. And the graph tells us that because you can draw a straight line through those points. So if you can draw a straight line through all the points, that means that that thing is travelling at a constant speed. It's not slowing down and then speeding up. It's just always moving 3 metres every second, right? Next one. Let's see. So we've got a distance of 0, 1, 2, 3, and the time is going 1, 3, 5, 7. So after 1 second, this thing had gone 0 metres. After 3 seconds, it had gone 1 metre. After 5 seconds, it had gone 2 metres. And after 7 seconds, it had gone 3 metres. Is that thing going at a constant speed? Well, it doesn't really matter if you can't do the maths, because if you've done a good enough sketch, you should have been able to draw a straight line through all the points. So you would know, yeah, it is going at a constant speed, because it's a straight line distance time graph. So it must have been. And it was, wasn't it? Yeah. After 3 seconds, it had gone 1 metre. After 5 seconds, yeah, it's fine. So did you do the final one? Or are you trying to quickly do it now? I've got distracted smelling my sourdough bread and I have absolutely no idea how much time I've given you, so I'm really sorry if I've gone too fast. But let's have a look anyway. You can do it with me. After 2 seconds, this thing was still at 0 metres, so it didn't move for 2 seconds. After 3 seconds, it had gone 3 metres. After 4 seconds, it had gone 8 metres. And after 5 seconds, it had gone 15 metres. So again, some of you will have just been able to see, okay, well, I know there's 1 second gap between 2, 3, 4 and 5. And I know that this gap is changing. Like the difference between 0 and 3 is 3, but the difference between 0 and 8 is 5. And the difference between 8 is 7. So what do we do? Well, you can't draw a straight line through these points, can you? It's not going to work. If you try and join up the first one and the last one, then the middle two aren't part of the line. And if you join up those two, you can't draw a straight line. That is not what is happening here. What you would have to do is you could draw a line of best fit through these points, but it would have to be a nice smooth curve like that. By Jove! A curve. What's happening? What's going on? Not a hypothetical question. Can you tell me what's happening? What is happening if a distance time graph shows you a curve? Well, hopefully some of you are saying, well, the speed is not constant. The speed is not staying the same. And yes, that would be true. This is where it takes me quite a lot of getting my head around this, actually. If I was doing this in an exam, I would have to go incredibly slowly, especially if it's an exam and you're really nervous. Let's say we've got a distance time graph that looks like that. Is that a good enough curve? I'm going to try and make it even curvier. Let's say that our distance time graph looks like that. What is happening there? And this is where in an exam I would have to go, okay, so time, I'm just going to do what we call like arbitrary units. I'm just going to split it up into kind of more or less equal portions. So after that much time, my first chunk of time, it hasn't gone very much distance, okay? Time has passed, hasn't gone very much distance. So that means it's going slow. I'm just going to be really vague just to get it into my head. I'm not going to worry about the maths yet. And then if you go to the very end here, so like we've sort of had 3 times more time passing, but how much distance has it gone? It's gone loads more than 3 times the distance here, hasn't it? Can you see that? Like here, a bit of time passes, not very much distance going by. Here, 3 times more time passes, loads of distance. And if a bit more time passes, suddenly you're right up here. So what's happened is this one's going fast, isn't it? A normal amount of time has passed and it's gone a really far distance. So that one would be fast. And that is what I would have to do in an exam, just to absolutely double check with myself. This thing is speeding up. It started slow and it ended up fast. So it's speeding up. Its speed is changing. So how do we find the gradient of that? Like if you get asked how fast was this thing going at this point, how do you find that out? You can still find the gradient of it, but what you have to do is you have to go to the point you want to find the speed of and draw a straight line. I will show you. I have prepared this. Here we go. Look, so here's a distance time graph, what's all curly. What you have to do is, if you asked, okay, what speed was this thing travelling at this point here, you have to draw a straight line so that you've got equal amounts of space between the line and the curve on either side. Imagine the curve as being like a little pivot and you're trying to balance the line on top of it, okay? So that distance there on the left and that distance there on the right between the curve and your line have to be the same. And if we extend that out as far as it can go, then the gradient of that line tells you the speed at that point, all right? This, the y-axis distance of your line, divided by this, the x-axis time, gives you the gradient of your graph at this point, as long as you've drawn it right and it's more or less exactly either side of the curve. Phew. So that gives you the speed of the thing at that many seconds, in just the same way that, you know, taking the standard gradient would. Let's do that again. So a point here, how would you do that? Because it kind of is almost a straight line, isn't it? Well, again, you would just have to draw a straight line so that there are equal amounts of space on either side. And then take a gradient of that line. So if it's going downwards, it doesn't matter, you can still do the y-axis divided by the x-axis. That bit divided by that bit, as it says on the PowerPoint, gives you the gradient of your graph, which gives you the speed of the thing at this many seconds. Really hard question for, I just got a new coffee supporter. Love it. Do you know? It might not be someone actually watching this lesson, but there's nothing better than halfway through a lesson, my phone just going, someone paid you. Right, yeah, really, really tricky question this, I think. When we talked about Usain Bolt last week, that's your sort of vague clue, if you remember that. Oh man, my sourdough bread, I'm getting a bit worried about it. Yeah, your difficult question is, why can't you just take the distance and time at this point and divide them? Do you see what I mean? So if that point there is, for example, let's do easy numbers. If that point is a distance of 10 meters after 5 seconds, if after 5 seconds that thing ran 10 meters, why can't, if you need to work out the speed at that exact point, why can't you just do the distance, which is 10 meters, divided by time, which is 5 seconds, to give you 2 meters per second? Why can't you do that? I think that's really tough. If you think it's really easy and you've already worked it out, well then just like and subscribe, would you? And I'll tell you the answer in a couple of seconds. But everyone else, I want you to think about this. Have you got it? I wouldn't expect you to be honest. But I've got to give you brain exercise, haven't I? You've got to become problem solvers, so it's all helping to build your brains up. The answer is, again, like, well, imagine a race that is, imagine a race where someone walks really slowly for the first 9 meters and then speeds it really fast, for example. Say they were going at 1 meter per second for the first 9 meters, and then for the very last meter they ran at what? Say they were, you know what I mean? Say someone started a race really slowly and then they suddenly sped up. If you just do the amount of distance, if you do 10 meters divided by 5 seconds, because it took them 5 seconds to get to that 10 meters. What you're doing is you're calculating their average speed, all right? Do you see what I mean? You know that it took them 5 seconds to run that 10 meters. So if you do 10 divided by 5, you're telling me their average speed over that 10 meters. But that's not really the information that you want. What this question wants you to do is find out how fast they were going at 10 meters. And you don't know that by just working out the time it took them to get 10 meters. You've got to take that gradient of that graph. Is that all right? Let's move on. You can't reply anyway. Okay, let's get to speed time graphs, because I did say that this whole lesson was speed time graphs. So let's fill in this little speed column here. Speed equals distance divided by time. You can see that. You don't need to ever remember equations, because look, the units are telling you speed, the units of speed are meters divided by seconds. So you know that to get meters divided by seconds, you've got to do meters divided by seconds, distance divided by time, okay? So speed equals distance divided by time. 0 divided by 1, 2 is 0. 3 divided by 3 is 1. 8 divided by 4 is 2. And 15 divided by 5 is 3. So let's plot a new graph of time and speed against each other. So let's put speed on the x-axis this time, in meters per second. And let's plot that. So remember, the distance time graph that we drew for this one was a curve, okay? Let's see what happens when we plot speed against time. Oh, it's a straight line. What? So this distance time graph was a curve, but the speed time graph of this situation is a straight line. What is happening, by the way? What is the proper physics word for something changing speed? You'll know the word even if you didn't think of it as being a very physicsy word. What's it called if something speeds up or slows down? Changes speed. It's called acceleration. In physics, you would actually say that, in real life, you say that something's like decelerating if it's slowing down, don't you? But in physics, you could call that negative acceleration. More of that next week. But anyway, yes, what is happening here is acceleration. This thing is speeding up. Its speed is changing. Yeah, you can see that its speed is changing. First, it was going at 1 meter per second, then 2 meters per second, and then 3 meters per second. So its speed is changing. So it's accelerating. But what kind of acceleration is this? Well, it's a straight line speed time graph. So first of all, it was going at 1 meter per second. Then it was going at 2 meters per second. Then it was going at 3 meters per second. What this graph is showing us is something called constant acceleration, which I start to find a little bit brain melty. So it's accelerating, its speed is changing, but it's changing by the same amount each time. Yeah? So it's constant acceleration. Okay. Cool. Have you got that? I just don't know why. I just do find this a bit weird, that something can be constantly accelerating. Its speed can be increasing, by the same amount each time. It didn't accelerate slowly and then suddenly go from like 0 to 60 in 2 seconds. You know what I mean? Right. Here I've written is a tough question so that you can practice physics or practice thinking about difficult things without crying, which are both very important skills. Here we go. So you've got two graphs here, a distance time graph, meters and seconds, and a speed time graph, meters per second and seconds. If the gradient of this distance time graph represents speed, which it does, I'm showing you 4 meters divided by 4 seconds equals, for example, 1 meter per second. So 1 meter per second is the gradient of this graph, and it's the speed that the object was going at. And the units of speed are meters per second, which they are. Can you see on this speed time graph, and this straight diagonal line is telling us that this thing is doing constant acceleration, can you see what the units of acceleration are? And if you can, if you're like, straight away, well, what's the equation for acceleration then? Go on. What's the equation for acceleration? If you can't see it, it really doesn't matter. This is all part of the process. I was the one in physics class, even when I trained to be a physics teacher. Like, I'm not even talking about when I was a kid. Even in physics class, when I was 28, just sat there nearly in tears because everyone else was like, oh yeah, I get it. And I was like, I don't get it. But that's not the point. The point is, think about it, brain exercise, and then I'll tell you, and then maybe you will get it. Or maybe it'll take you a bit longer. It doesn't matter. Toying with the idea of going to get my bread knife and cutting it at the end of the lesson so that we can all discover whether it's cooked properly or not, because I know that you're just not going to be able to sleep tonight unless you know. Have you got it? Doesn't, like I say, it doesn't matter if you haven't. The units of acceleration, oh, apparently I was thinking that I would just show you that on the board. Here we go. So, speed equals distance divided by time. Let's change this into speed now. Here we go. So the units of speed are meters per second. Obviously, it could be different on different graphs, but we will say meters per second. The unit that we normally measure time in is in seconds. So you're doing meters per second divided by seconds. The units of acceleration are meters per second. Meters per second. And if you like maths and you know about fractions, then what you can do, I am not a maths teacher, I'm going to explain this really badly, but that's like saying meters divided by seconds, okay? Let's get rid of all this graph here. Let's just do it. I don't know, I'm not sure. I'm not a maths teacher. This is the only problem with physics, is that most of you in my classroom would come in and the maths teacher would have done all this bit, so I wouldn't have to bumble my way through it. But we're doing meters per second, like meters divided by seconds. And when you're working out fractions, let's just say that, yeah, so meters divided by seconds is meters per second divided by second is the same as saying meters divided by second times seconds divided by I'm not going to bother. No, I've chickened out. The units of acceleration are meters per second, and how you write that is meters per second squared. I'm so sorry. Even a physics teacher should know how to show you that on the board. But another way of saying meters per second is meters per second squared. And that is the unit of acceleration. And because to work out the gradient, you did speed divided by time, that is also the unit of acceleration. Change in speed, which was on the y-axis, divided by time. But we'll do more about acceleration next week. Right, another little tricksy question for you. Speed equals distance divided by time. Rearranging this, I've put maths later, gives distance equals time times speed. Hard to say, hopefully fairly easy to understand. If speed equals distance divided by time, you can rearrange that and you get distance equals time multiplied by speed. Can you spot a quick way to look at a speed time graph and know the distance travelled? Speed time graphs can do something awesome that distance time graphs can't do. What can speed time graphs do that distance time graphs can't do? There's a really easy, quick way of looking at a speed time graph and knowing the distance that the thing travelled. Can you see it? Distance equals time multiplied by speed. You got speed on the y-axis, you got time on the x-axis. So that would, multiplying a time by a speed would give you the distance. That's your clue. It's the area under the graph. How good is that? So the area underneath this graph here, for example, this thing travels at 1 meter per second for 4 seconds and then stops. So you end up with this rectangle. And if you do 4 seconds times 1, you get 4. So 4 seconds times 1 would be the time times the speed, which gives you the distance. So the distance travelled is 4 meters. And the same with this one. This thing was travelling at 3 meters per second for 3 seconds and then stopped moving. So you could probably work out that if something's moving at 3 meters per second for 3 seconds, it travels 9 meters. But you could look at the area underneath this graph and know that, look, there's 9 squares. It's good, isn't it? And you can do this for any speed time graph. You've got to be a little bit careful if it's a diagonal line. So for example, if you got this graph here where it goes up diagonally for 3 seconds and then it goes flat for 3 seconds, and you got asked how far did this object travel between 3 and 6 seconds? Well, between 3 and 6 seconds you could just draw a little triangle like that and find out the area that is underneath the graph between 3 and 6 seconds. So it's 12 meters, right? It's 4 meters per second times 3 seconds, which gives you 12 meters. In the first 3 seconds, there's something you've got to be a little bit careful of to do with finding the areas of triangles. So you would still have to do the sort of base times the height, but you've got to remember to divide it by 2. Okay, so you find the area of that rectangle, but the graph is a triangle, so you'd have to halve it to find the area of that graph. So that would be 6 meters. Is that okay? And I don't think, and often it'll ask you how far it travelled in 6 seconds, and then you would have to add those together. And they're looking to see who's forgotten to divide by 2. It's all very mean. But there you go. That's how you find the distance travelled using a speed time graph. Shall we do a little quiz before we finish? Ready? Let's get this rubbed off the board. So I've got 8 graphs here, and I'd just like to tell me what is happening. In fact, yeah, I'm going to make it just a little bit harder than I did before. Actually, we'll start slightly easier. I've given you multiple choice on the bottom. I think some of them, yeah, after this one, I'm going to take that multiple choice away to make it a little bit more challenging for you. Can you just tell me, please, what is happening in this graph? You've got a distance time graph. Distance is always going to be on the x-axis and time is always y-axis and time's on the x-axis. Does this graph show, so you've got a steep diagonal line going from 0 upwards diagonally. Does this graph show, please, constant speed or constant acceleration or no movement? Is that constant speed, constant acceleration or no movement? It's a distance time graph. The answer is, have you got it? Constant speed. It's going at a constant speed. It is travelling at speed. Time is going by and it is travelling some distance. And the distance keeps changing. And it's changing by the same amount each time because it's a straight line. So that is the answer A, constant speed. Well done if you got that. Right, now I'm going to take the multiple choices away. Oh, brutal. I did this yesterday on Facebook and I just felt like it was a little bit easy. What does this graph show? You've got a speed time graph this time. And it's a straight diagonal line going from 0 up diagonally. What does that graph show? Clues? Is the speed changing? Is the speed of this thing changing? And if it is, what's the word for speed changing? And what kind of? So this thing, the speed is changing, right? The speed is going up. You can see it starts at 0 meters per second and then maybe it becomes, its speed is 1 meter per second, then 2 meters per second. So it's speeding up, it's accelerating, and it's doing constant acceleration because it's a straight line. So it's accelerating by the same amount each time. That was a tricky one to make only the second question. All right, what about this one then? What's happening here? We've got a distance time graph. Distance, like I say, on the y-axis, time on the x-axis, and your line is just going along the 0 line. It's just going along the x-axis at 0. What is happening there? What's that thing doing? It's... Got it? It's staying still. It's just staying still. Time is going by, but it's not travelling any distance at all. So it's staying still. What about this one? I've got 8. The whole point is that you start off getting them wrong, ideally, and then you start to get them right, because that's like me teaching you stuff, innit? You've got speed, you've got time, and you've got a diagonal line going through the 0 point, going up, a shallow line. What is this thing doing? This is a speed time graph. A diagonal line going from 0. Is it speed changing? And if it is, how is it changing? It's accelerating. It's speeding up. It's accelerating and it's constant acceleration because it's a straight line. This next one. You've got a distance time graph and let's say this is meters 1, 2, 3, 4. The line just goes across. It just stays at 4 meters. What is this thing doing? Pause it if you're watching on catch up. Hello if you're watching on catch up. Thanks for watching on catch up. And then I'll tell you the answer. If you're watching live, sorry. It's staying still again, isn't it? It's staying still because it's just staying at 4 meters. Time is going by and it's just staying 4 meters away from whatever the arbitrary 0 point is. So this thing is not moving at all. This one, 3 more to go. Speed time graph, and it's the same thing. You've got a flat line. It's a speed time graph, and you've got a flat line which looks like it's starting at, let's say, 3 meters per second. What is that thing doing? Got an answer? You got the amount of words that you need? It's, well, is it moving? Yeah, it's definitely moving. It's going at, let's say, 3 meters per second. But its speed is not changing. It's going at a constant speed. That's what a speed time graph looks like if something is going at a constant speed. All right, 2 more. What about this one? You've got a distance time graph, but it's a curve. Distance time graph, but it's a curve. What's happening? Sourdough bread, you smell so good. I am going to try and cut you at the end of this lesson, which is imminent. I sounded a bit threatening. I'm sure it's looking forward to it. Have you got the answer? What is going on? Well, it's moving, isn't it? Time is going by and it is travelling a distance, so it has some sort of speed, right? But it's not travelling at a constant speed, is it? If it was travelling at a constant speed, it would be a straight line, and it's not, it's a curve. So if something's not travelling at a constant speed, it's the same shape as the one that I did on the board, wasn't it? It's actually speeding up. So it's accelerating is what it's doing. It's accelerating, it's speeding up. More on acceleration next week. And finally, what is this one doing? Speed time graph, and the line is just along the x-axis at the bottom. What is that thing doing? Got it? It's, well, what is it doing? If you said it's travelling at a constant speed, I guess you're not wrong. Oops. I guess you're not wrong to say it's travelling at a constant speed, because its speed is constantly 0 meters per second. And I guess 0 meters per second is a speed, but I think it would be more correct to say that this thing is not moving because it has 0 speed. It's not moving. Okay, so yeah, I would say no motion for that one. Whew. Well done, you lot. Right, that is the end of my IGCSE lesson on speed time graphs. I am going to go to my Facebook page to see if any of you have commented, because when I'm live on YouTube, there are no comments, but if you're watching live, you can go over to my Facebook page and I'll always have a post at the top saying, please say hello to me here if you want. If you're watching on catch up, hiya, thanks for having watched this on catch up. Obviously, if you're watching on catch up, then there will not be probably a post at the top of my Facebook page at the moment, so it would be kind of pointless you commenting on that. But you might still want to listen to other people's comments, because sometimes they can be very interesting. I'm watching the comments like, don't think anyone's been watching it. All right, yeah, just to let you know, spoiler, there are no questions here that will help your physics understanding. Bastian is here. Hello, Bastian, welcome. Welcome. I say that like you haven't had a science day. You've been here the whole time. And Amelia says, Kitty has decided to have a nap today instead of listening to this. Rude. Oh, and you've been practicing your physics on the trampoline. No way. Got my flick. Jump back into my hands. Wait, what? You've been practicing on the trampoline and got my flick. Jump back into my hands and then onto my hands. What is the difference between jumping into your hands and onto your hands? I don't know. Anyway, thank you for that. My mind is boggling. I cannot think how that works, but it sounds very impressive. If you want to support me, you totally can. In fact, a couple of people have signed up while I've been doing this lesson, which is incredibly cheering. So how it works is, everything that I do is free. These IGCSE Physics lessons are free, and they're saved on my website for free. The printouts are free. The homework PDF, which I will try and get done in the next few minutes actually, so you can start your homework, which is like past paper questions that you should be able to do after you've watched this lesson. That is free as well. And I just say, can you go to my coffee page? There's a link to it on YouTube. You can go to my About section on YouTube, or you can go to the big blue button that says sign up on top of my Facebook page and click sign up and pay me £5 a month. And I'll even send you nice things to say thank you. I will send you Digital Science magazine. At the moment, if you're watching live, if you sign up with £5 a month, you'll get the Acids issue of my magazine, which is the very latest one, which is huge. I'm not going to I'm going to do my whole big ad because my throat's getting a bit sore and I want to cut my sourdough bread. But it's really good. And you get some rainbow glasses, which I don't often mention, but they're actually diffraction glasses. And we do learn about diffraction at GCSE Physics as well, so they'll just be fun. But yes, thank you so much. Could not do this at all. Just really couldn't do it without people signing up to support me. Would have to be a teacher in a school, which would be fine. Right, I'm going to do it. I'm so excited. I'm going to go and get my bread knife and cut my sourdough bread. So, because some of you, like Bastian, come to my lesson that is this, my IGCSE Physics lesson, but you also come to my All Ages lesson. And last week we made a sourdough starter to learn about yeast, and I have just made my first ever loaf of sourdough bread with my first ever sourdough starter. And as I say that, I'm thinking, I think I've undercooked it, and I think it's going to be a massive disappointment. But it smells amazing. I'm gonna give it a go. I'm gonna do it while you're here, because why not? If it turns out perfect, I'll be really cross that I didn't show off in front of you, won't I? And it's not going to be edible next week. This is telly, isn't it? This is live as it happens. Cutting of bread. If you're watching on catch up, unbelievably, some people are still here. A lot of the people who are watching live have not gone away. I know. I'm as amazed as you are. But then if you're watching on catch up, you're watching this not even live. What are you doing? Being excited by my sourdough bread, that's what you're doing, and I'm very grateful. Here we go. Look, let's have a look. Don't ask me for a recipe because I didn't use a recipe really. I just mixed some of my sourdough starter with 500 grams of bread. But there's no shop bought yeast in here. There's no sugar in here, shop bought sugar in here. It's just that sourdough starter mixed with bread and water. Oh my days. Dudes. This is one of the happiest days of my life. Look at that. Oh my God, it's perfect. And it smells incredible. Oh, wow. Thanks you lot. Thanks for sticking around. Oops, just flashing you my very messy office. So from me and from Stephen's first child, Stephen's the name of my sourdough starter, I named it, I couldn't help myself. Bye bye, and now I'll get your homework done and I'll see you next week. Bye.